In this question we consider a slightly oblique off-center collision. So particle 1 approaches particle 2 and just on a line that's just going to clip its outer edge, so a distance of its radius away from the center, so a distance r away from the center, and at the point of collision the two centers are separated by 2r, of course, because it's twice the radius and they're both the same size. The particles are of equal mass and diameter. If the coefficient of restitution of these conditions is 0.6, determine the resulting motion of each particle and the percentage energy lost due to impact. So we need to break this up into a 2D problem. Defining a different coordinate system, we can choose normal, tangential, we can call them. Normal being the line of the collision, or the axis between the two particles joining the centers, and tangential being the one perpendicular to that. So initially we consider the normal coordinate system, and we say that our initial momentum is m1 times v1 brackets n, so the normal component of the motion of the first particle, plus m2 v2n, so the normal component of the motion of the second particle, and then that is equal to the momentum in the normal direction after the collision, so m1 v1 dashed n, where v1 dashed is the motion after the collision, and the same for v2 dashed, where v2 dash is the motion after the collision. So this is our first equation, and if we put in the values, we can say that this is 6 cos 30 plus 0, because the particle 2 is at rest initially, so that one's initially at rest, it comes in here, and these are our remaining two unknowns, so v1 dashed n and v2 dashed n. We also have the coefficient of restitution, which is in the normal direction, so v2 dashed n minus v1 dashed n divided by v1n minus v2n. And if this is all equal to 0.6, we have a simultaneous equation, because we have two unknowns and two equations. So we can compute that the final speeds of both particles, or the final normal components of the motion of both particles, are as follows. Now, doing the same in the tangential direction, we can see that the initial the particle 2 is stationary, so we're looking at the tangential component of particle 1, so m1 v1t, and that must be equal to m1 v1 dash t, because as you remember, you've got the particle coming in here, it collides, and v2 goes off in that way, so v2 goes that way, v1 goes this way. This is particle 2 and this is particle 1. So because of the nature of how we define the problem, this was our normal component, that was our normal direction n, this is our tangential component t, then particle 2 only has a normal component, it doesn't have a tangential component. So the motion of the second particle, m2 times v2t is equal to m2 and v2 dash t is equal to 0. So there is no momentum of the particle 2 in the tangential direction. Particle 1, however, we can work out its momentum in the tangential direction as 6 sine 30 because of the resulting motion, 3 meters per second. So v1 dashed is combining the velocity we found from the analysis in the normal direction, 1.039 squared plus 3 squared. Square root is 3.17, and for v2 dashed, i.e. the exit speed of particle 2, it doesn't have any component in the tangential direction, so it's just 4.16. Once we have these two velocities, we can work out the angle between their motions to be 19.11, and we can work out the energy loss. So if we look at the energy before the system, in terms of the initial speeds v1 and v2, we have 18, and since mass is constant, we can retain m as an unknown. And after the collision, in terms of v1 dashed and v2 dashed, has 13.88 m. And because it's a ratio, the m's cancel out. 18 minus 13.68 over 18 means that we have a 24% energy loss in the collision.